Okay, so first up on the list is the sort of technology that we're using inside of our register file, a so-called static RAM. And at the heart of the static RAM, I hope you recognize that diagram. It's a little bistable loop made by a little loop of inverters. And that loop will reliably remember a value. So if I have a 0 on one side, I'll have a 1 on the other side of this little loop, the other side being the other of the two nodes. And this little loop, as long as I keep it plugged in, well, even if there's a little bit of noise and one of these voltages gets slightly corrupted, it'll be restored by the logic gates. And it's quite happy. And you can see here that to read the information out of the loop, what we're going to do is to, I've got some information stored in this cell. In fact, I've stored a 1 bit in this cell. So one of these two nodes is a 1, and the opposite, the 1 on the other side of the inverter is a 0. And the way I read information from this cell is I'm going to put a 1 on the word line, the line that will turn on these access field effect transistors, and basically couple this bit line here to the information that's stored in that particular cell. If I wanted to read out a different cell, I would be turning on a different word line. And the reason it's called a word line is that this structure here is replicated horizontally, in our case by 32 times, because we're going to read out 32 bits in parallel to read out an entire word. So this word line actually will end up going to 64 different access FETs. So when I assert a particular word line, I'll get 32 bits out the bottom. And then what happens is once I turn on these access FETs, these very small these FETs are made out of these inverters are made out of reasonably small FETs, and to keep the size of the SRAM small. And so what I've done is I have this line that, in our case, will connect to 32 different bits in a column. And so I have some capacitance here to drive because of the capacitance associated with the drain of the access FETs. And so as these small transistors are busily trying to charge and discharge this line, so this is a little slow. Being not nearly as fast as a logic gate. So there's this sort of an analog circuitry going on here. And in fact, what I do is I build a fancy analog circuit called a sense amp that listens to both bit bar and bit, looks for a small difference between those two values because they're going in opposite directions. And as soon as that difference is a small number of millivolts, I don't have to wait for them to get to be legitimate logic values. I'm not building a digital circuit, I'm building an analog circuit that's sort of trying to deduce digital values from small changes in voltages. And so I get my answer out reasonably quickly, but because it's an analog circuit. Even more analog-y is this idea that I'm going to write simply by putting a very strong driver, something that has huge FETs in it, that can supply a lot of current, and I'm basically going to punch this little feedback loop in the nose. I'm going to turn on the FETs and say, you're now a 1, and this little inverter is saying, no, I'm pulling it up, I'm pulling it down, it's a 0. And I'm going, no, 1. and what happened, and the volume of my voice is meant to represent the amount of current that's being supplied to that node, and I can actually flip the value of that cell by writing a strong 1 and a strong 0 here. And so this is very analog. You're saying, what happened to this dynamic, the static discipline? And you're saying, we're not living in that world anymore. Okay, so, and these cells, it takes 6 transistors for each one, and then there's a sense amp circuitry and all that. So it's a clever bit of engineering that gets the job done. They're hard to design. I mean, they're not something that ordinary mortals should do. You have to be a fairly clever analog designer with some years of experience to get these to work reliably, depending on what the manufacturing line is doing and the temperatures and the power supplies and things like that. We can build a multi-port SRAM simply by having multiple bit lines and selecting and multiple word lines that will basically allow us for each of the different read ports to select the output of a different cell onto the line. And there's some little details here about rearranging the circuit slightly so that the capacitance of the bit lines doesn't end up flipping the cell accidentally if we tried to read it out into too many of the read ports at the same time.